Hello, good morning, brother. So yesterday we were doing Taylor series, okay, and we went extensively in order to know how Taylor series are being expanded. Okay, so we know how to find the radius of convergence of the series, and a few more things like the question that you asked yesterday, and a few more things we'll do it separately in the series kind of topic because that that will be too difficult for us to assimilate in this entire thing. Okay. So yesterday we were doing Taylor series, and a few things we've done. Like we've done how to find the radius of convergence. Also, we know that how to write the domain of convergence for a particular power series. Okay, and also that we've done a few things that is are implicitly asked. So, for example, your function whenever it is singular at some points, let's say z1, z2, z3, and so on and so forth, you know that you just have to find what the center of the power series and just the distance from the nearest singularity. And if you know that distance from the nearest singularity, this is the maximum radius of convergence that you can draw for a particular center of power series. So if your center is here, let's say at z equal to 0, and you encounter your first singularity at let's say zi, which is at distance say let's say this is at distance del, then your radius of convergence would be del because beyond it it is going to encounter the singularity zi. So indirectly also a few things you can know, and this is what is the most exploited kind of thing in your exams because this is an easy thing to see, right? Now a few more top points and then we'll move to the Laurent series. So one of the best things that we can do is once we know that your function is analytic, I told you on the very first day, and let's say it is on region R, it is analytic, then we can expand that particular function in terms of the power series. What is the better advantage? Since you know that there are derivatives, if Z is analytic, then the derivatives are also analytic. You can also write one of the most powerful thing that a power series. Okay, so alternatively, I'm using power series. Like Taylor series is a special case of power series only. So this is what is the power series. And instead of the n, if you just replace dz upon at z equal to z naught, this is nothing but it is equals to your Taylor series. Okay, so Taylor series is a kind of power series. Okay, so power series summation an z minus z naught raised to power n can be differentiated term by term. Can be differentiated term by term. Term by term. You can say within the region R. What is the region R? Region R is the region of holomorphy, or you can say analyticity. Yeah, you can say that domain of convergence. So where your power series is convergent in that particular zone, you can do what? Let's say if my power series I can write about z equal to z naught and it is convergent in this particular domain, that is this particular domain or this particular region R, then I can say that in this particular region R, I can differentiate it term by term. So I like differentiating function would imply differentiating the power series representation of that particular function about z equal to z naught. Okay. Similarly, you can integrate by term also. So you can, the similar statement above, you can integrate term by term as well. You can integrate term by term as well. Term by term as well. But within what? But within the circle of convergence or domain of convergence. Within domain of convergence. Okay. Now, just a simple question to you. Let's say if I have two power series, let's say my function fz is there and there is a function gz. Let's say the radius of convergence for this is r1, radius of convergence of this is r2. What will be the radius of convergence of the sum of these two particular two functions? Let's say I have a function fz, I have a function gz. The radius of convergence of fz is r1, radius of convergence of gz is r2. What will be the radius of convergence of this sum of the function? Any ideas? I mean, am I audible now?
whichever is larger, matlab.
Whichever is minimum, whichever is minimum, larger. Okay, so you see, देखो कैसे देखोगे? Let's say if I'm expanding, let's say for convenience, I say that I'm expanding about z naught and I'm expanding about z naught. Okay, and let's say I have two power series representation. At z naught, function fz can be expanded such that it is in the radius is r1. And let's say if I have function gz, it can be expanded about z equal to z naught, and let's say entirely the radius is r2. Okay. Now, what is the problem? This particular function, that is gz, is completely valid, or its power series is completely valid in this particular region. However, you'd find that fz is not analytic, or fz cannot be expressed in terms of power series for all these points. So, in order to have an agreement, what the best agreement can be, I can declare that why not should I expand my power series in the radius r1? Because in the radius r1, gz is completely fine, fz is completely fine, in the sense that if gz and fz both can be represented in terms of the power series. So if my power fz is centered about z naught, gz, and I have to write the if I have to write the power series representation of fz about z naught, if I have to write the power series representation of gz about z naught, and if I know that their radius of convergence are r1 and r2 respectively, you can fairly see that both of them would agree on this particular radius of convergence. So always remember, if you have you can say if you have two power series, let's say fz can be written in some power series representation, let's say an z minus z naught raised to power n, and let's say z can be written in a power series representation summation bn into z minus z naught raised to power n, and the radius of convergence is r1 r2, then the sum, or say, let's say subtraction, will converge for minimum of the both. Are you getting my point till now? I hope it is clear to you. ये चीज समझ में आ गई?
Yes, sir.
ठीक है. For all those entire functions, like for example, e raised to power z was an entire function, sin z was an entire function, cos z was an entire function. You can use the same Maclaurin series that you used to do in your uh, uh, real analysis. In real analysis, your function e raised to power x can be expressed as 1 plus x square upon 2 factorial, so on and so forth. Similarly, your sin x can be represented as, I think, x minus x cube upon 3 factorial, x की power 5 upon 5 factorial, so on and so forth. What you do, तुम क्या करोगे? You just write a few series that you know. Like for example, cosine x you know. For example, ln 1 plus x you know. So all these series you put them down in your notebook so that you remember them. Okay. So these expressions will hold um, like the way they were in real analysis only. Why I'm saying this? Because otherwise you'll have to go differentiating term by term. Like you have to do this way. That will also give you the same result, but this will be a too tedious thing to do in examination, and it is too time consuming as well. Okay. Okay. This point I have already stated that, for example, if your what should I say? If your function is non-analytic at, let's say, point zi's, and it is centered at z naught, your function is non-analytic at, let's say, point zi's, or it is singular at point zi's, and if I want to expand this particular function about z naught in terms of a Taylor series, I fairly know that zi's will create a problem. So what can be the radius of convergence? The radius of convergence would then be, let's say, in this sense I'm making, let's say I'm saying ki all the singularities are real only, then, and let's say z naught is this point, then the maximum I could do is, maximum I can do is, I can make this sort of circle. That is, the circle will be of the radius modulus of z1 minus z. Okay, this is clear to you? I think this is very much clear. Okay, should I move further? Okay, so there is a series called as binomial series. Let's say 1 plus z raised to power p. It can be expanded as 1 plus pz plus p into p minus 1 factorial, p minus 1 upon 2 factorial z square, plus p into p minus 1 into p minus 2 upon 3 factorial z cube, and so on and so forth. And the nth term could be written as p into p minus 1 E dash 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 p minus n minus 1 upon I think n factorial z raised to power n dash dash. You can clearly see here it is 2, here it is 1, here it is 3, here it is 2. So if the denominator is 2, here the term would be 1, that is less than 1 less than the denominator. Here it is 3, here it is 2, so 1 less than 3. So clearly the nth term will be of this way. Okay, so you will find, you will see this is your binomial series and uh, it is only valid for mod z less than p. That is, for this particular series, the radius of convergence would be 1. Okay, absolutely fine. Okay. Okay, so what you can do, so for example, understand my point that Taylor series representation to an analytic function is unique. Taylor series representation of an analytic function is unique. Since it is unique, what you can do? So if I say that this is my region R, what I can do, I can expand uh, my function fz in terms of power series about z equal to z naught. How would I do that? I would calculate this particular thing. Okay, I would calculate this particular thing. Okay, but understand the point that since it is unique, and if at all you are able to write a binomial series representation around this, that would mean the same thing. What I'm saying, what I'm making a point here is, it is not necessary that always you'll find derivatives. Let's say finding a derivative is a difficult thing to do. What you can do, you can simply do one thing. You can simply go for a binomial series about z equal to z naught. This both will converge because Taylor series to a function is unique. So उसका एक ही representation आएगा. समझ रहे हो? Z equal to z naught के about Taylor series uniquely represent होगी. Since unique होगी तो मतलब उसका expression एक ही होगा. If at all you are in a position that you can easily find a binomial series about z equal to z naught, do it. It is not going to uh, create any kind of problem. That binomial series will actually be equal to the Taylor series. मैं लिख देता हूँ Taylor series representation of an analytic function is unique, so one can obtain you can say that expansion directly using a binomial expansion, using a binomial binomial expansion wherever it is possible. So for example, I gave you an example also. The example was, let's say if I'm supposed to find what is the Taylor series expansion of tan inverse x. Okay, and I'm in a fix as to what should I do. The derivatives will be too difficult for me to see. For example, the first term will be fine. The second term will be 1 upon 1 plus x square. The second derivative, and so on and so forth will become very difficult for you to assess. What I'm making a point is, see, देखो tan inverse x का एक बार derivative करोगे, that is absolutely fine. ठीक है. Second time derivative करोगे, okay, not bad. But beyond it, it is very difficult for you to do all these things in examination. What would you instead prefer? Just do a derivative. Okay, just do a derivative. So what you will get, you will simply get 1 plus 1 upon x squared. I don't think there is a problem in this. Okay, and you can clearly see that if I just differentiate, one of the things that I will tell you lately is what is the derivative? 1 upon 1 plus x square, or you can write tan inverse z also. This will come as 1 plus z square. Okay, the derivative will come as 1 plus z square, and this will become non-analytic at plus minus iota. So I'm writing the expansion above in the radius of convergence of 1. Okay, so it is fairly easy to see if my power series is defined, all my higher order derivatives will be defined, and my first order derivative becomes analytic at z equal to plus minus iota. So therefore, I'm choosing the radius of convergence as 1. Is it clear to you? Now, what I can do is, I clearly know that f0 is equal to 0. So if I write fx is equal to tan inverse x, and this will be your f dash x, can I not write f dash x as 1 upon 1 plus x square? Bharat, samajh mein aaya tha? And can I not write it in this fashion? I can write 1 plus x square raised power minus 1. And can I not expand it binomially? I can expand it binomially. So I will expand it binomially. Minus x square plus x की power 4 minus x की power 6 plus x raised power 8 dash dash dash. This you can simply verify on your own. This would be the case. Are you getting my point? And there will be some constant.
Yes.
Sorry, this will be it. Okay. Now what you can do, you can integrate it. So fx would give you x minus x cube upon 3 plus x raised power 5 by 5 minus x raised 7 by 7 and so on and so forth. Till now, I think it is clear to you. Now, what you can do simply is, you can simply, since you've integrated, you just need to find the constant of integration as well. So what would be the constant of integration? Just place 0 all the way. So 0 minus 0 plus 0 minus 0 dash dash dash. And f0 is already 0. You can clearly see that your c will become 0. So therefore, I'm not writing. So your function, that is tan inverse x, can be written in the power series, that is x minus x cube upon 3 plus x raised power 5 by 5, so on and so forth. In fact, you will find that this particular series is convergent even at r equal to 1. Even at r equal to 1. I told you on the very first day that at r equal to 1, you may or may not have convergence. You don't know about r equal to 1. You clearly know that if I'm writing that your series is convergent, let's say for r less than 1, you can say that, and you can say that, let's say your series is divergent for r greater than 1. So r equal to 1, you are inconclusive. On the very first day, I told you D-Lambert ratio test and all those things, that r equal to 1, you don't know. And even if you don't get into all these things, you just there is a problem here. That is why I'm saying probably I'm at a loss of a theorem right now, and I will not be able to dictate you right now. But just keep this in mind, that if somebody asks you what will be the value of tan inverse 1, let's say somebody asks you the series representation. So this particular series representation will give you what? 5 by 4. Are you getting my point? Does anybody have any problem?
Yes, sir. It's clear, sir. Sir, at r equal to 1, we have the singular point plus minus iota also. No?
Right. So that is why I'm saying, just for sake of right now, just accept this fact. Okay. There's a theorem called as Abel's theorem that I would come in the series part. Okay. So right
Okay, sir.
now,
Okay.
just accept the fact. Okay. Uh, for now, this was as in just examination. Right now, I'm at a loss to say a more rigorous thing for it. But right now, if something like this pops up in your examination, you have to write it. We'll take around 2 to 3 lectures on series, because I'm seeing the questions level are increasing right now. So, for example, somebody to ask this question in physics examination is too a difficult thing for a physicist to do, because this is something that I don't even teach in mathematics also. I refrain from doing all these things because sum of series is mostly not asked. The answer is 6. But the point is this: ki, how they're asking, I don't know. But if they're asking, then certainly the level is going up. So series, in any case, we'll do 3 lectures over it, and there I will tell you all these small things there. But right now, just accept the fact that this particular series will become convergent, since tan inverse 1 is pi by 4, and this entire thing is 1 minus 1 by 3 plus 1 by 5 minus 1 by 6. So how differently you can see things, like you cannot believe this is it, but this is. I mean, how can somebody believe that 1 minus 1 by 3 plus 1 by 5 minus 1 by 7 plus 1 by 9 minus 1 by 11 added for an infinite sums would give you a pi by 4? So that is too difficult thing for you to judge in examination. Okay.
Yes, sir.
Okay. We'll come to this particular point later. I'm not able to explain it proper because right now I don't have the excess of theorem. Like I cannot tell you in between of complex analysis, all those things, because it is a different story altogether. Okay, so we'll do all these things in our series part, and probably we'll do it on any Sunday or Saturday, Sunday. It would hardly take 3 to 4 hours, and we'll finish it off. Okay. Uh, Now let us move to something called as Laurent series. So what happens? What happens when your function is non-analytic at a point? So I already stated that if my function is non-analytic at, let's say, z naught, I cannot expand a Taylor function in form of a Taylor series about this point z equal to z. So if
सर
I'm, हाँ बेटा बोलो.
सॉरी टू डिस्टर्ब यू सर। एक क्वेश्चन और था सर, जैसे आपने हमने जो जितने रेशियो टेस्ट वो सब किए थे डाइवर्जेंस और कन्वर्जेंस के लिए, जिसमें हम लेस देन वन और ग्रेटर देन वन करते थे, सर इस केस में तो हमारा ठीक है, फर्स्ट डेरिवेटिव में वन बाय एक्स स्क्वायर प्लस वन आ रहा है, बट हम सभी केस में वन ही क्यों लेते थे सर?
वन ही क्यों लेते थे ऐसा बोल रहे हो?
जी।
देखो उसके पीछे रीजन है कैलकुलस के अंदर. ओके, सो दैट पार्ट आई वोंट बी एबल टू एक्सप्लेन बिकॉज हो क्या रहा है वहां पर. अच्छा, तुम ये कहने की कोशिश करो ये वन ही क्यों होता है ऐसा?
यस सर,
मतलब
हमेशा
जैसे
सर वन को ही क्यों रेफरेंस ले रहे हैं?
वन को रेफरेंस इसलिए ले रहे हैं क्योंकि देखो होता क्या है. कैसे समझाऊं, देखो कोई चीज की, इट इज अ वेरी डिफिकल्ट क्वेश्चन बट लेट मी टेल यू. होता क्या है, व्हाट वी डू इज, इफ आई एम सेइंग दैट माय सीरीज इज कन्वर्जेंट. चलो अब एक बार हल्का सा आइडिया देता हूँ ना. I think it will not go anywhere, but let me try. So if I'm saying my summation n is convergent, then limit n is zero. This is a theorem in mathematics. Okay. If I'm saying summation n is convergent, then limit n is zero. Converse not true. Understand my point? Converse is not true. So for example, I may have limit 1 over n as 0, but summation n is not convergent. This I will come over it in the series part. But overall, understand the point that if summation n is convergent, then limit an will be zero. And किसी चीज की लिमिट जीरो होने का मतलब क्या है पता है? कि an और जीरो का डिस्टेंस छोटा होता जाएगा. समझो ना, कोई चीज जीरो के करीब जा रही है. दिस इज व्हाट इट मींस. लिमिट an इज जीरो टेंडिंग टू जीरो. टेंडिंग
यस
टू
सर।
जीरो मींस an और जीरो का डिस्टेंस एप्सिलॉन से कम होगा. सो कन्वीनियंट वे ऑफ सेइंग इज कि एक टाइम के बाद an वुड बिकम लेसर देन 1. Why would I say lesser than? See, because anything which becomes less than 1, anything which becomes less than 1, like in this fashion, if it becomes less than 1, so what I would do is, or less than 1, so let's say it implies what? It implies if I'm saying that your limit an plus 1 upon an is 1, so I can write that, that would be too difficult thing for me to. So I think that would be too difficult thing. Right now, just don't go about it because it will be too difficult thing. But overall, I'll make you understand this particular thing because see,
ओके सर, ओके।
होता क्या है देखो, what we do is we use all these kind of arguments in let's say in series. Okay, and uh, basically it will be too difficult for you to follow right now. That is why I'm leaving it for now. I'm leaving
ओके
it.
सर।
We'll come to it on series part. Okay, so you keep your question in reserve. This I'll answer you. Probably you may be able to follow. Many people may not be able to follow it, but otherwise I'll try my level best because I know this argument you will not get in any case. We'll do it anyway. Okay, we'll do it anyway.
ओके।
Okay, चलो एक बार के लिए आगे बढ़ते हैं. So for example, if at all my function fz is analytic at z naught. Now I'm at a fix. Now I'm at a fix because now I cannot expand at z equal to z naught a power series of the form a Taylor series. Okay, so how to circumvent this kind of problems? So what you would do is you will make you will exclude this particular point from your evaluation. So when you exclude this particular points, basically except this point, you are including other points. Okay, you're including other points. Such representation requires you an annular region. Such, I can say, such things would require you an annular region. Okay, annular region मतलब समझते हो, मतलब दो डिस्क के बीच का कोई रीजन या दो सर्कल्स के बीच का कोई रीजन. सो दिस इज एन एनुलर रीजन. देखो कैसे समझते हैं या फिर ऐसे समझते हैं. Till now the power series representation that I was doing was of this form. Okay, so this was your power series representation. This was fairly, you can fairly see that this was a Taylor series. What if I have a power series representation of the form this way? So there is a singular, there is a regular part, and then there is a singular part associated with it. Now you can clearly see that at z equal to z naught, there is a part which is having singularity at z equal to z. Okay, so at z equal to z naught, this part will become singular, isn't it? This is fairly easy to see that this is a regular part, but overall this will become singular. So any such representation, any such power series representation would be valid in which region? This is your question. Understand my point. I'm saying now you're asking for example. So let's say I'll give you an example. Let's say if I say my function is sine z divided by z, or let's say z square. Okay. Let's say this is my function. So what you do, you expand in this form, z minus z cube upon 3 factorial, z raised to power 5 by 5 factorial, so on and so forth, divided by z square. What you will get? You will get 1 over z, isn't it? And then you will get some terms in z square, sorry, z upon 3 factorial plus z raised to power 4 upon 5 factorial and all those things. So you are having some regular part. Like here you can see that you are having some regular part, but you are having some singular part also. At z equal to 0, this is non-singular. This is singular, sorry. This is not analytic. At z equal to 0, this will blow up, isn't it? So there is a possibility that a function may be represented in this manner also. Can you accept this fact that a function may be or may be expressed in this fashion? Are you getting my point till now? Yes or no? अल्पना को समझ में आया?
हाँ भैया.
Okay. And since it may be represented in this fashion, the natural inquiry that would ask is, what is that radius of convergence where you can do this thing? I mean, obviously you can clearly see that z naught has to be excluded, because see, z naught, if it's there, then it's not going to make sense. Okay, so let us see how to go about it. So let's say this is your power series. This power series is convergent in R1, and let's say this converges in R2. So what would happen? Z minus Z naught will be, this particular series would be convergent for mod Z minus Z naught less than R. Okay, absolutely fine. And this particular series will be convergent when I can write 1 upon Z minus Z naught mod as some W, isn't it? So this will be convergent for all W mod less than R2. मानते हो बात? इस 1 upon W minus 1 upon Z minus Z naught को एक काम करो, W लिख दो. So this will be a series summation V minus N mod W. And this particular series will be convergent for what? Mod W less than R2. And what you can say, mod W is what? Mod W is again 1 upon Z1 minus Z2. So you can write that Z minus Z naught ka mod less than, greater than 1 upon R2. Are you getting my point till now? It implies both of these, both like the sum of it. This particular series and this particular series will converge in what radius? It will converge in this radius. Okay, is that clear to you? And it's very easy to see that z naught has been removed, because at z equal to z naught, it will be equal to 0. Okay, and 0 cannot come between two positive numbers. Are you getting my point? Say at z equal to z naught, this will become 0. Would z naught lie in this region? No, because if z naught lies in this region, there's a problem here. So there are possibilities where you are required to expand a function in an annular region. So this is an annular region. Can you understand? Like let's say this is your point z equal to z naught. I'm saying the radius must be greater than R2, 1 upon R2. Let's say this is your 1 upon R2 if I say. So let's say this is your 1 upon R2. And then I'm saying that another radius is R1. इसका मतलब क्या हुआ? What does it mean? It means that this representation, this series representation that I'm writing right now, I'm telling you right now, this power series is this sort of power series representation okay, is valid in what sort of region? In this region. What is this region? This region says, I told you on the very first day that read it in the modulus fashion also, read it in the distance manner also. What does z minus z naught mod means? It means what is the distance of complex numbers from z naught? So it says that the distance of complex number from z naught is should be greater than 1 upon r2. So it should lie outside this circle, isn't it? So outside this circle. So what does this first statement mean? It means that the radius of convergence for this particular series says that I am fine if you take mod z minus z naught greater than 1 upon r2. So this is what I'm shading. But what does this say? It says, okay, stop here itself. I am saying I would be convergent for mod z minus z naught less than r1. So it says that I would be convergent for this particular region. Okay, in fact, inside also. Okay, so it says that I would be convergent. The latter part in the inequality says I would be convergent in this region. Okay, so what would they both agree to? What would they both agree to? They would agree to saying that okay, we are both agreeing on this particular annular region. Are you getting my point? So this particular annular region is something that they both would agree to. Are you getting my point? So this such type of representations are called as Laurent series representations. Such representations are called as Laurent series representation. So Laurent series representations are valid for some annular region, as I have stated just before. Are you getting my point? Yes or no? ये चीज समझ में आई कि नहीं? Just the name
जी
Laurent
भैया
series. And what would Laurent series look like? Laurent series would look like there would be some term which is completely regular. There are no issues about it, and there will be some terms which are called as a principal part. These are called as principal part, and this is your regular part. This is your completely regular part or completely analytic part. And I'll come back to the problems that Bharat is also asking. But only point is, I'm right now, I can completely understand all those difficulties. But the point is, for me to write all those things will be too difficult for you to follow right now. That is why I'm not writing it up. And secondly, there are two that is too rigorous for a mathematical physics course too. But still, I will try my level best in series part. Right now, just concentrate on this Laurent series because this is fairly very important. Okay. I hope this is clear. Okay.
Yes,
So
sir.
Laurent series would look in this kind of fashion. Okay. Now, so let us move ahead and let's say how does it helps us? Okay. How does it helps us? So if I'm having certain singularities that I already taught you, like poles, removal singularity, and so on and so forth, uh, you can clearly see that those singularities can also be understood by the help of Laurent series representation. How to do a Laurent series representation, I will tell you. Don't worry about it. I'm just trying to make a point. Uh, if you really want a particular definition, that I would give that also. Let's see if I'm supposed to give a definition. So here it is. So consider I'll give you a definition so that in the next lecture we'll do the thing. So Laurent series, consider an annular region. Consider an annular region between two concentric concentric समझते हो ना मतलब एक सेंटर circle C1 and C2 C1 and C2 centered about Z naught centered at Z equal to Z naught and the function fz is analytic in the annular region okay annular region at each point z in the annular region fz can be represented by a convergent series uh, uh, which I can say is in this fashion. In a convergent series, fz is equal to an z minus z naught raised to power n plus b minus n z minus z naught raised to power minus n. Okay, and this I'll write summation n equals to 1 to infinity, and this I'll write summation n equal to 0 to infinity. Okay, and it's not required for you to know ans, but I'll write it here. And what would be bn? Bn would be this. Don't worry about it. All these things I'll tell you later on. But right away, you don't have to worry about all these things. What we'll do a certain kind of trick in order to develop Laurent series for some functions that we could do very easily. Right away, don't get disturbed with this. Okay. So this is your an, this is your bn. So understand the fact that if your function is singular about a point, you can not expand it in terms of Taylor series. Since you cannot expand it in terms of Taylor series, what you can do? You can write a Laurent series representation, in fact, about z naught in a radius of in an annular region. In an annular, let's say this is your C2, this is your C1. Okay, in this region, I'm saying. I hope it is clear to you. Okay, so we will discuss how to find the singularities in by using the Laurent series expansion in the very next lecture. Okay, I hope it is clear.
Yes, sir.
समझ
सर
में आई
इसमें
बात?
क्वेश्चंस तो शायद
हाँ
ज्यादा
हाँ
क्लियर हो
हाँ हाँ मैं अभी
उसके बिना
next session में we'll do only questions only. Okay,
ठीक है
okay, okay.